Okay, so let's continue our discussion on solution of Pfaffian differential equation. So we have seen three methods. The one is method of inspection, and second one is variable separable, and third one is one variable separable. And the method four is homogeneous equation. So in this, so a function p of x comma y comma z is said to be homogeneous of degree n if p of lambda x comma lambda y comma lambda z equal to lambda power n is said to be of degree n. So it is lambda power n into p of x comma y comma z. So the equation, the Pfaffian differential equation, p of x comma y comma z dx plus q of x comma y comma z dy plus r of x comma y comma z dz equal to 0 is said to be homogeneous. Is said to be homogeneous of degree n if the functions p, q and r are homogeneous of degree n. P is a homogeneous of degree n, q is a homogeneous of degree n, and r is a homogeneous of degree n. In that case, we call this equation, say let's name this equation number 1. This Pfaffian differential equation is a homogeneous equation of degree n. So in such a case, we substitute y is equal to ux and z is equal to vx in 1. Also their derivative, that is dy is nothing but u into dx plus x into du, and dz is equal to v into dx plus x into dv. So my equation 1 implies, so it is p of x comma ux comma vx dx plus q of x comma ux vx. Now in the place of dy, it is now u dx plus x du plus r of x comma ux comma vx, and in the place of dz it is v dx plus x v dv equal to 0. Now since pq are homogeneous equation, and we are substituted y equal to ux and z is equal to u vx, hence there is some common term, some x power n in p, q and r, so we are taking out and cancelling. So the remaining will be p of 1 comma u comma v. So again I am collecting the terms with respect to derivative. So I am considering the derivative with respect to x, that is dx, and here again it is dx, so it plus u into, so it is where it is, so it is u into dx, so it is u into q of 1 comma u comma v plus again it is r into v, so it is v into r of 1 comma u comma v whole into dx plus terms derivative with respect to du, so it is again x into q of 1 comma u comma v into du, and with respect to dv it is again x into r of 1 comma u comma v dv equal to 0. Now by dividing by, it is p of dividing by p of 1 comma u comma v plus q of 1 comma u comma v into u plus v into r of 1 comma u comma v, we get it is dx plus so it is x du divided by let's name this as some a of uv. So my writing will be little bit reduced. So x du plus, and this one the last one will be, so it is x dv divided by one more term this q of 1 comma u comma v into du. Again this let's make it correct. So x into r of 1 comma u comma v into dv divided a of uv equal to 0. Oh, by taking this x to this denominator, we get it is, or just multiplying by 1 by x, we get it is dx plus q of 1 comma u comma v du divided by a of u comma v plus r of 1 comma u comma v dv by a of u comma v equal to 0. Now this can be solved by method 3. That's one variable separable with respect to here one x is separated, so we can solve this by method 3. So let's take a problem. Let's verify that following verify that equation yz into y plus z dx plus xz into x plus z dy plus xy into x plus y dz equal to 0 is integrable, and find its solution. So now given differentiable equation, so let's name this one. So to verify it is integrable, we should find let's take first x is equal to p comma q comma r, where what is p? It is nothing but yz into y plus z. Q is nothing but xz into x plus z. R is nothing but xy into x plus y. Now, so verify that it is integrable. It's actually integrable. So verification of integration x dot curl x equal to 0 is left as an exercise. Okay. Now first check whether this p, q, r are homogeneous. So p of lambda x comma lambda y comma lambda z, which is nothing but it is lambda y into lambda z, because p is something but yz into y plus z, so it is again lambda y plus lambda z. So lambda is common, so it is lambda cube into yz into y plus z, so it is nothing but lambda cube into p of x comma y comma z. Similarly, you can observe cube of lambda x lambda y lambda z, which is equal to lambda x into lambda z into lambda x plus lambda z, which is nothing but lambda cube into xz into x plus z, which is nothing but lambda cube into cube of x comma y, and r of lambda x comma lambda y comma lambda z, which is equal to lambda x into lambda y into lambda x plus lambda y, which is nothing but lambda cube into x into y x plus y, which is nothing but lambda cube into r of x comma y comma z comma y comma z. Hence the p, q, r are homogeneous of degree 3. Q and r are homogeneous of degree 3. Now, so as we see in the theory part, now we need to substitute. Y is equal to ux and z is equal to vx in the given differential equation and its derivative, that is dy is nothing but u dx plus x du, and dz is nothing but v dx plus x dv. So we get so it is ux dx into ux plus dx dx plus again x into, so it is x into z, so it is x into vx, x plus vx, and now dy is nothing but u dx plus x du. The last term is x into y, so it is x into ux into x plus ux, dz is v dx plus x dv equal to 0. Now let's observe this is from this, it's x into x into x, so x cube, here x cube, again here x cube, yeah, and here again x into x cube, again here at x into x into x, yeah, x cube. So x cube is common and I'm getting cancelled. So then my remaining term, and I'm clubbing with respect to the derivative dx, that is now it is u into v into u plus v plus now here with respect to dx it is now, yeah, v into 1 plus v, so v into 1 plus v into u plus now here it is again u into 1 plus u into v whole into dx plus now with respect to du, so it is now v into 1 plus v into, yeah, again it is x dx, yes, yeah, x dx, yeah, yes, so x du plus so it is again u into 1 plus u into x dv, u into 1 plus u into x dv equal to 0. So my equation now reduced to equation in x, u and v. Now divide this equation throughout by x into uv, u plus v plus u into v into 1 plus v plus u into v into 1 plus u. We get it is dx by x plus now. So I'm dividing this these two together. We get it is now, yeah, it is now v into 1 plus v x and du plus so it is u into 1 plus u dv whole multiplied by x and divided by so this term, so by solving it will be 2uv into 1 plus u plus v and this x, so it will get cancelled, so equal to 0. So we get that is dx by x plus, so using partial fractions, so we get it is 1 by u minus 1 by 1 plus u plus v into du plus 1 by v minus 1 by 1 plus u plus v dv equal to 0. So we can find this using a partial fraction. So now that is so it's multiply 2, so it is 2 dx by x plus so now it is plus the last this one, that is dv by v minus derivative of, I am clubbing these two terms, to d of 1 plus u plus v divided by 1 plus u plus v. Now derivative this will be du plus dv, so it is du minus du divided by 1 plus u plus v minus dv divided by 1 plus u plus v. Okay, so which is equal to 0. Now on integrating we get it is 2 into ln x plus ln u plus ln v minus ln of 1 plus u plus v, which is equal to say ln c, that is nothing but x square into u into v divided by 1 plus u plus v, which is equal to c. Now this substituting your u and v, we get it is x square. Now u is nothing but y by x and v is nothing but z by x, which is equal to c into, so I am taking this term, so it is 1 plus u is nothing but y by x plus z by x. So rearranging we get it is x y z equal to c into x plus y plus z is the required solution of my given differential equation. So now let's move forward to find and see the next method. There's the method 5. So we have seen 4 methods. Method 5. So this method is known as Natan's method. So here consider the different Pfaffian differential equation E of x comma y comma z dx plus q of x comma y comma z dy plus r of x comma y comma z dz equal to 0. Now, and the first thing, first we treat here z as constant. Then this equation 1 is reduced to 1 into p of let's say p dx plus q dy equal to 0 because we treated z as a constant. Now suppose we find the solution of this this equation as say phi of x comma y comma z equal to c1. This is the solution of this equation. Solution of this equation as phi of x comma y comma z equal to c1. So then the say this is equation number 2. Now the solution of equation 1. So that the solution of equation 1 will be after form say capital phi of some phi and z, because this phi is the equation solution of p and q. So including and one more variable z, we will get a solution of 1. Let's denote it by capital phi of phi comma z equal to c2, where here c1 constant and here c2 constant. Now combining these two, say this is 3, combining this 2 and 3, we get a solution in terms of say capital phi of x comma y comma z is equal to xi of z. Now this is the solution by combining 2 and 3, and hence it will be a solution of my equation 1. When this this z is some function of z. Now to determine the function, to determine this of z, so we observe that if a given variable x a fixed value, we are giving some fixed value to this x, say alpha, say x is equal to alpha. Then this equation is reduced to capital phi of alpha comma y comma z is equal to xi of z. And since we take x is equal to alpha, and our differential equation becomes, it is q of alpha comma y comma z plus dy plus r of alpha comma y comma z dz equal to 0, and this will be the solution. This will be the solution of this differential equation. Now, if we find the solution of this differential equation in separately, it will be upon some k of say some function k of y comma z, k of some y comma z equal to c. Say, let's name this. Okay, yeah, we are naming this is equal to 4. Yeah, not this. This is equal to 4, and this is equal to 5. And say this is equal to 6. Now, see, this is the solution. This let's name not this as 4. Let's name this as 4. Now, this fourth one is the solution of this, as well as this the sixth one is the solution of equation number 5. So 4 and 6 are the solution of equation number 5. Hence this 4 and 5 must be equivalent. This 4 and 6 are the solution of 5. Therefore, they must be equivalent. So by rearranging, so by substituting, okay, in the from this 4 and 6, they are equivalent. So we eliminate the variable y between this 4 and 6 and obtain the expression for xi of z, because see, this is the function of yz, this is the function of alpha yz. If you eliminate y between these two equations, we are getting equation in terms of z, that is nothing but xi of z. Now substituting this xi of z in this equation, equation number 4, substituting xi of z in this equation, we get the required solution. So let's take a problem. Verify that the equation z into z plus y square dx plus z into z plus x square dy minus xy into x plus y dz equal to 0 is integrable and find its primitive. Now, so let's name this equation as 1. So we have x is equal to, now it's p comma q comma r, and that is nothing but z into z plus y square, z into z plus x square minus x into y plus y. So verifying x dot curl x equal to 0 is left as an exercise. So assume that it is now proved, and hence equation 1 is integrable. Now take, so in the discussion of method 5, we see that we have treating one variable as constant. So we here I will treat y as constant, and hence we get equation 1 becomes, so it is z into z plus y square dx minus xy into x plus y dz equal to 0. Now now divide this equation throughout by z into z plus y square xy into x plus y. We get it is dx by xy into x plus y minus dz divided by z into z plus y square, which is equal to 0. It's equal to 0. Now simplifying using a partial fraction, we get it is 1 by x minus 1 by x plus y dx minus, so again this is 1 by z plus y square minus 1 by z into dz equal to 0. So on integrating we get it is 1 by x dx, so it is ln x, so minus 1 by x plus y dx, so it is now ln minus x plus y, because derivative this x plus y is nothing but 1, so again it is minus 1 by z plus y square with respect to dz, so it is now again ln of z plus y square minus again it is ln z, which is equal to, it's now plus ln z equal to say ln c. So by rearranging it is now x into something is there any wrong mistake? It's a plus and it's minus. Plus and minus. So it is x into z plus y square divided by z into x plus y. Say this is equal to f of y. In the theory we discussed, we taken it as xi of z. So here I am taking f of y. So if we take so in the above discussion we taken x is equal to alpha. So here I am taking z is equal to 1. So instead of z is equal to alpha, we are taking z is equal to 1 in equation 1. In equation 1, that's in my given differential equation. This, so we get it is z into z plus 1 dy minus x into y plus x plus y into dz. Okay, so no, I'm taking z is equal to 1. So I'm getting, it is 1 into 1 plus y square dx plus 1 into 1 plus x square dy. So it is 1 into, so therefore it is 1 plus y square dx plus 1 plus x square dy equal to 0. Let's verify this once again. So now by rearranging this, so take to this side and divide, so you will get it is, or divide this by 1 plus y square and 1 into 1 plus x square, you will get it is dx divided by 1 plus x square plus 1 dy divided by 1 plus y square, which is equal to 0. Now if you integrate this, now this is 1 by 1 plus x square derivative, that is nothing but tan inverse of x plus this is tan inverse of y, and this is nothing but a constant. So let's take this constant as tan inverse c. So for our simplification, now tan inverse x plus tan inverse of y is nothing but tan inverse of x plus y divided by 1 minus x into y, which is nothing but tan inverse of c, tan inverse of c. Now by just since it's a constant, it's taking a reciprocal and making a new constant, that is 1 minus x into y divided by x plus y, which is equal to a new constant c1. Constant, and c is again a constant. The constants is, that is we got 1 minus, wait a second, so equation number 3, let's see, equation number 4. Now so if you observe this this solution is a solution of this and this solution and this solution are similar in such a way that if I take z is equal to 1, it's a one form of this solution. one form of this solution in some certain case, or we can in certain case. So therefore this equation 2 and equation 4 are equivalent. So by equating them and eliminating x, we get f of y is equal to 1 minus c into y, 1 minus c into y. So 1 minus c into y. Now substituting this in equation 2, we get it is now x into z plus y square is equal to z into x plus y into 1 minus c into y. This is the required solution of the given differential equation. Now moving forward, let's solve. Let's see one more method. That is method 6. Method 6. This reduction to an ordinary differential equation. Reduction to an let's write it short form, ordinary differential equation. So in this method, we are reducing the problem of finding the solution of a partial differential of a type or Pfaffian differential equation of type pdx q dy plus rdz equal to 0. Say equation number 1 to that of integrating an ordinary differential equation of first order in 2 variables. So suppose it has a solution say f of x y z equal to c. Say let's name this equation 2 is a solution of a given differential equation. Now this 2 represents one parameter family of surface in a space. Now this integral surface, this is so one parameter family of surface, and this surface will be intersect in a single infinity of curves by a plane z is equal to x plus ky. Say the k is a constant. So as I vary this k, I am getting different planes. When intersecting with this surface, I am getting different curves or infinity of number of curves. Okay. Now using this, my equation 1 becomes it's a p of x comma y comma z. So it is x comma y comma. Now z is nothing but z is we are taking in terms of this substitution k dx plus q of x comma y comma k dy is equal to 0. So we are eliminating z between this 1 and 3 using 1 and 3. So we are getting p dx q dy without z, by eliminating z. Now using the solution of this is the equation number 4. Using the solution of 4, we get a family of surfaces. So we get a family of surfaces 2. Solution of 4. So suppose general solution of this is nothing but say y of x comma y comma k is equal to say some constant. This is the solution of this equation 4, that is p of x comma y comma k dx q of x comma y comma k dy. So when I vary this k, so this will represent, say let's name this as equation number 5. And okay, one more step. So the point on axis of the plane 2, this plane 2, that is intersecting with z is equal to x plus ky is determined by y is equal to 0 and x is equal to c. So Therefore my this equation 5 becomes phi of x comma y comma k is equal to phi of c comma 0 comma 0 comma k. So as I vary this k, as you seen this, so my planes changes and I'm getting different of curve. So when k varies, my equation, this equation, say is equation number 6, it will represent the family of curves to the point y is equal to 0 and x is equal to 0. So if c is also varies, we obtain a family of curves through each point on the axis. So if we eliminate k from this equation 6 and equation 2, we get the integral surfaces, that is phi of x comma y comma z minus x by y, which is equal to phi of c comma 0 comma z minus x by y. So it will be the solution. So let's take a problem. So integrate the equation. So it is y plus z dx plus z plus x dy plus x plus y dz equal to 0. Now verify it is integrable. So x is equal to now y plus z, z plus x, x plus y, that is nothing but p comma q comma r. Now put z is equal to x plus ky, z plus x plus ky, and then we get this equation 1. Let's say this is equation 1. It is reduced to dy by dx plus 2x plus k plus 2 y divided by k plus 2 into x plus 2 ky equal to 0. Now if you observe, this is nothing but again an homogeneous equation in x and y. So by substituting y is equal to vx and dy is equal to v dx plus x dv, this equation becomes 2 dx by x plus 2 kv plus k plus 2 into dv divided by k v square plus k plus 2 v plus 1 equal to 0. So on integrating we get it as, and rearranging, so it is x square into kv square plus k plus 2 into v plus 1, which is equal to some constant. Therefore my solution phi of x comma y comma k will be equal to k y square plus k plus 2 into xy plus x square. Here I resubstituted v is equal to y by x. So that is now phi of x comma y comma k in terms of xy, that is z minus x divided by y, which is equal to x into y plus y into z plus z into x, and phi of c comma 0 comma z minus x by y will be equal to some c square. So by combining these two, we get it is xy plus yz plus z into x plus c1, z into x, which is equal to c1, where c1 is we just rename it c square as c1, again a constant. The solution of the given differential equation. Hence, we have seen a 6th method to solve to find the solution of Pfaffian differential equation. The first method is by inspection, second method is variable separable, third one is one variable separable, fourth one is homogeneous equation, fifth one is an Nathan's method, sixth one is reduction to an ordinary differential equation. Thank you.